All right, today we're going to talk about matrix products. So previously we talked about transformations. So for example, let's take the transformation where you stretch by a factor of 2. And then we're going to take the transformation where you contract or shrink by a factor of 2, or it's the same thing as multiplying times 1/2. And in this particular case, if you apply these transformations sequentially, it should be no surprise that we'll just end up what we got started with. These two transformations are inverses of each other. They undo each other. So we're going to end up with exactly what we started with, which means the total transformation from beginning to end, what's the single transformation that describes that? That's the do nothing transformation. And we can encode the do nothing transformation by just looking at what happens to the standard vectors. So the 1, 0 goes to 0, 1. And sure enough, 0, 1 goes to 0, 1. Oops, rather, this is 1, 0. So we're going to end up with this nice matrix. And this matrix has a particular name. This is called the identity matrix. So in general, the identity matrix or the identity transformation is encoded by a matrix that just has 1s on the diagonal and has 0s everywhere else. So if you're in higher dimensions, it's just going to look like a diagonal matrix with 1s on the diagonal, and this just means do nothing, right? If you apply a vector to this, it'll just sit there and do the same thing. It's the machine that just spits out exactly what you put in. You can think of this as multiplying by 1 because in some sense that's really what it's doing. And so what we want to be able to do is we want to be able to take these two transformations, which have their own matrix encoding, and use those two matrix encodings to somehow shortcut the process of doing this sequence and get the identity transformation. Because after we apply the sequence, it's the same thing as doing nothing. It's just the identity transformation. So how do we do that? Well, that's going to be done with matrix products. So how do matrix products work? So if we want to multiply two matrices, or more accurately, let's think about this as applying two different transformations. One thing that's going to be a little strange is we're going to apply the transformations from right to left. So when we write S times T times V, this really means we're going to start with V, then we apply T, and finally apply S. So transformations are going to be written from right to left. So what that means is if we want to mimic the example we got up here and test this one out, when we multiply the matrices together, if we want to take the same process, we're actually going to multiply by this 2, 0, 0, 2 matrix on the right. And then we want to multiply 1/2, 0, 0, 1/2 on the left. And so this means this mimics this. If we multiply these together, this is going to be the same thing. What we should get is we should get this. This is indicative that it's the same thing as doing nothing, and we should get the identity matrix. So let's go ahead and multiply these together. And I'll show you how that's done. So to multiply matrices, let's first take a quick advertising break. We're going to apply the principle when we multiply matrices. We're going to apply the principle of RC Cola. Okay, this is a real thing. Okay, it's actually in the mid-store. But what this means is if we want to find the entry, for example, let's find the first entry. So this entry right here is going to be the first row, the first column entry. what we're going to do is we're going to take the first row of the first matrix and the first column of the second matrix, and we're going to multiply those together. All right, so let's keep going. So this is going to be 1/2 times 2. So again, that's 1/2 times 2 plus 0 times 0. And then to do the next one, to do the first column, second row, we're going to do the first column times the second row to get this entry. Whoops. Yeah, that's right. Hold on. Sorry. Let's try this again. First row, second column, we're going to get over here. So let's do that. So we're going to do 1/2 times 0, 1/2 times 0, plus 0 times 2. And then to do the next one, to get this right here is the second row, first column. So what we're going to do is on the left rather, we're going to take the second row and the first column. And we're going to multiply those together. So we're going to take 0 times 2. We're going to add 1/2 times 0. And then finally, for the last one, we're going to take the second row and the second column. And we'll get 0 times 0 plus 1/2 times 2. All right, so if we simplify all this, we'll end up getting 1, 0, 0, 1. And sure enough, that's exactly what we expected. We expected that if you apply these transformations in order, you'll get the same thing as doing nothing, which is encoded by the identity matrix. So let's go ahead and talk a little bit about matrix products. So one thing that's important is because a matrix product corresponds to transforming things from right to left, it's important that the output of the first transformation matches this. So what that means is the number of columns of the first matrix has to match the number of rows of the second matrix, because the transformation is going to output the number of rows. Every matrix, when you can think of it as a transformation, the number of outputs is the number of rows. So this means that always when you do matrix multiplication, these two numbers have to match. So if you view this as the first matrix might be m by n, this means m rows. You have to apply the principle of RC cola, m rows times n columns. And this is n rows and L columns. The output here is going to be m by L. So whatever you end up here is going to be m by L, precisely whatever's on the outside. Again, the principle of RC cola applies. So you're going to always have the rows indicated first and the columns indicated second. And if you have multiple matrices and you want to multiply them together, right? It always has to be the case that the size of these matrices, these inside ones, always have to match. And the end result is just going to be whatever's on the outside. And again, that's because the output of the first matrix has to be the input of the next. And likewise, the number of outputs of the second matrix has to be the number of inputs for the next. And then all you're left with is just what the number of inputs and outputs are for the first and last ones. And that's going to tell us exactly the size of the final matrix. If you can't do this, then we're just going to say it's undefined. You can't do the transformation. Okay, so we've covered a lot of our bases about how these matrix products work. Let's do some examples. We're going to do some examples that are slightly more enlightening. So we're going to take these two matrices and multiply them. And this corresponds to the transformation of reflection So what we're going to do is, what does this transformation do? This is going to flip over the x. So whatever the x is, it's going to flip it over the y-axis, and it's going to make it negative. So this is going to turn that first basis vector to the negative side. And then the second one, this one's a little strange. This is shearing. So what this does is this is going to move the second basis vector over to the right a little bit by 2. So it shears by a lot. But it's still going to have the same height. And the x vector is going to be the same. So what happens if we apply these two transformations in sequence? What happens? How can we describe that with a single matrix? So we're just going to multiply these matrices together. So we're going to do the same thing as before. We're going to take the first column and first row. So we'll end up with 1 times minus 1, 1 times minus 1. And then we're going to add 2 times 0. So that's just for the whole, that's for that first entry. We're going to keep going. We're going to do the first row and the second column. We end up with 1 times 0 plus 2 times 1. That's for the first row, second column. Let's keep going. Second row, first column is going to be 0 times minus 1. So that's 0 times minus 1 plus 1 times 0, 1 times 0. And that gives us that entry. And then finally for the last one, we're going to take the second column and the second row, second column, and we're going to end up with 0, 0 times 0 plus 1 times 1. So again, that's 0 times 0 and 1 times 1. And all together, when we simplify this, what do we get? We get that the single transformation that we get is minus 1, 2, 0, and 1. Okay, so that's good. So this doesn't really, this matrix doesn't have a name. This goes to show that you can create transformations and then code them with a matrix that necessarily in and of themselves don't have a simple geometric explanation. So this idea of reflecting and shearing just has this encoding. What this means is the matrix encoding algebraically is a lot more robust than the geometric descriptions. It still can be thought of geometrically as some sequence of things that you're familiar with, in this case, a reflection and a shear. But it's not something that is easily seen. So this is what happens when you have these before and after graphs where you get this kind of weird twist, turn, stretch. You get matrices that look like this that aren't fit any of the patterns that we did last time. So let's do one more example that's going to illustrate a very, very important point. And what we're going to do is we're going to do these same transformations, but in reverse. What we're going to do is we're going to multiply minus 1, 0, 0, 1, and 1, 2, 1. So this differs from what we did before. We're changing the order of the transformations. What we're doing is we're going to do the shear first, and then we're going to apply the reflection. All right, so we're going to see what happens now. So we're going to go through it again. I'm not going to talk through it this time, but you can race me if you want. And let's simplify this. All right. Just as a pro tip, one thing you might want to do is to actually put your finger whenever you're doing a row and column, and then move the one on the left, you're going to move that one sideways, and move the one on the right up and down. Okay, so we get this matrix. That wasn't hard. This seems tedious and kind of boring. But the interesting thing that I want to point out is you'll notice that there's a mild difference between these two matrices, notably right here. There's a difference. It's very subtle, but one has a minus and one doesn't. And what this means is that if you actually apply these transformations in a different order, you're going to get different results. That sounds obvious when you think about it in terms of transformations, but if you just thought about this as just multiplying matrices as boxes of numbers, it may not be very clear that if you multiply them in different orders, you'll get different results. So probably the biggest warning to have about matrix multiplications. So we're going to put this in a big warning box. In fact, we're going to enlarge this. Okay, we're going to make a big warning. All right, so the big warning is that in general, if you multiply two matrices, it is not the same as multiplying the reverse. So in math language, we say matrices don't commute. So commute is a phrase that just says that AB equals BA. So it is possible but not always that this is true. So it's possible that two matrices commute, right? This is what we call commuting. And so matrices in general don't commute. You can't just switch the order. This is probably the one thing that's very different about matrix multiplication and matrix products is you're not allowed to switch the order however you want. Okay, so before we wrap up for this session, let's take some time just to go over some matrix properties. So one property that we haven't gone over is called the transpose. This is just very nice when you want to talk about matrices. So the transpose of a matrix, this is probably just best defined by example, says that you're going to make the columns rows and the rows columns. So like this. So this would be the transpose. So if the one on the right is A, we're going to call this one A transpose. So this is what this little T here means. This T right here, this T indicates the transpose. This hasn't come up yet, but it makes it easier to write and talk about matrices, especially when you just say, oh, this is just the transpose. So now that we have matrix products, we have matrix sums, we have matrix vector sums, and inverses, we can talk a lot about kind of the arithmetic properties. So what are properties of matrix arithmetic? And what I want you to think about from here on out is kind of how, when you have a case where you want to do this, think of a matrix not as a box of numbers, but think of it as a transformation that you can add, subtract, multiply, and kind of divide. We'll get to that later. And you just need to keep in mind which properties are true and which ones are not. So most of the properties you think would be true are. So for example, if I take two matrices and add them together and apply a vector, that's the same thing as just distributing. I can take the matrix, the transformation, apply the vector, and then add it to the next one. So matrices are also associative, meaning that if I have three matrices I'm multiplying together, I can multiply them in any order I want, as long as I can multiply them in any order I want, in the sense that you can do one part of the product first and replace it. So in this case, I can multiply A and B together and take whatever that is and then multiply it by C, as long as the order of the matrices are the same. So as long as you maintain the order that the matrices come in, you can actually do the arithmetic. You can group them up however you want. There's also kind of the FOIL. So things FOIL out. So this works exactly as you expect. You just FOIL it out as you would normally. But the main catch here is you have to make sure that the order is maintained. So whatever's on the left here is also on the left whenever you FOIL it out. And whatever's on the right, it stays on the right when you FOIL it out. The next couple ones are maybe a little unintuitive. They have to do with transposes. So if I take two matrices and I multiply it and then I take the transpose, that turns out to be the same thing as just multiplying the transpose but in reverse order. And in a very similar way, the same thing actually applies for inverses. So keep in mind, when you think of inverses, when you think of the fact that the inverse is undoing things, you are going to undo them in the reverse order that you apply them. So AB means let's apply B and then A. So what does that mean? To undo that, I need to take A inverse and then apply B inverse. Oops, I did that backwards. You have to first apply A inverse and then apply B inverse. Because the order that you reverse things in, that you undo them, that you invert them is the reverse than you originally applied them. So another one, this one may be a little more intuitive, but maybe we haven't seen it before. If you take the transpose of a sum, that's the same thing as just taking the transpose of two individual ones. So that one should be intuitive. You just flip them and then you add them. Right. And the last one that's kind of important to keep in mind is that you can multiply a matrix by a constant value, right? So in some sense, this is just scaling everything in the matrix by K. And you can write it as K times A, but that really means take every entry in A and multiply it by K. But the big thing to keep in mind about all these properties, it is not true that AB equals BA. So this is the one where you probably can't use your intuition. So every time you want to think about changing the order of things, you should think about, am I changing AB versus BA? And the reason you can't do that again is because that corresponds to applying transformations in a different order. So this is kind of a simple example showing that. And this isn't that complex of an example. These matrices are not that far out. They're very simple. And so in general, if you pick two random matrices and multiply them, they're not going to give you the same result one way or the other. So in most cases, they don't. When they do commute, they're very special. So that's the last property to keep in mind. Most of these other things should be intuitive from algebra. Just keep in mind that matrices don't commute. So that's it for this time. There's just a lot of practice of these and applying your geometric intuition to multiplying matrices. So go ahead, go nuts, and have fun.